If you recall, yesterday we integrated over a simple closed curve, two different vector fields. In one case, we got 0, and in the other case, we got 25 pi. Now, here we got a here we got a graphing machine that will calculate up for us some line integrals. The value of the line integral is approximated up in this corner up here, 78.5393. That's 9 pi. So notice what we're integrating is the vector field 2i plus xj, and the curve over which we're integrating is 5 cosine t, 5 sine t, from 0 to 2 pi. What we're visualizing on this graph, notice that all this red down here, that is where the dot product is positive. So that's all that positive stuff. These white areas are where it's close to 0, and then the blue area is negative values of the dot product. So we can see all this red overpowering the blue parts and coming up with our massively positive 25 pi. Because I made the circle so big. And this is the reason yesterday I was dealing with this. Oh, by the way, we can do that. I was thinking of this demonstration, forgot that I had used a 5 before, switched to a 3, wrote 9 pi, and then wrote 5, because that's what I actually been using in class. So upstairs it was a 3, and when I went down 2 flights of stairs, apparently it turned into a 5. I didn't know that down 2 floors meant +2 in radius. Yeah. So notice that we have all this red part and just very little blue part. So overall, we got a positive value for the line integral. If I change the j component to a 1, notice that the amount of red and the amount of blue is about the same. And that's why when we calculate this, we get not just 0, but -0. That's what makes this very strange. We get -0. I don't know why it puts -0. I have a feeling that because it's approximating, because this is specifically line Riemann sum calculator. So that's the whoever created this. Someone said, oh, here's my line integral calculator. And someone's like, actually, you're approximating this with a Riemann sum. And then they're like, fine. They just crossed out the integral and put Riemann sum calculator. That's probably why it says -0.0000. Probably if you had it display some more decimal points, there's going to be some small negative value. It's like when you don't use the TI-84 so much, but every once in a while, the TI-84 says 0 by saying something like 2 times 10 to the -14. And some students be like, all right, 2 times 10 to the -14, but they don't understand that the E means times 10 to this, so they just write 2E -14. And like they tell on themselves. That's fine. So here's a handy line integral calculator. Here we get 0, and in the red part, we see the positive, where in both horizontally and vertically, the graph is kind of, the path is kind of going along with the vector field. And then here in this upper part of the circle, when I say upper part of the circle, I mean above a line with a slope of 1/2 that's going through the center of this circle. You can see where it's kind of evening out here and changing from positive to negative. And then up in the upper half, we get that blue part indicating the negative values. And the amount of positive value and the amount of negative value are the same, canceling each other out. Here's a quick line integral visualizer using a line Riemann sum. Any questions? Comments? Snide remark. So whether or not we get 0, whether or not all that stuff balances out is dependent on the vector field. This is going to depend on the vector field. The first vector field, 2i plus 1j, this vector field is conservative. That means it's a gradient field. That means it's the gradient of some function. So this vector field here, 2i plus 1j, this is a conservative vector field. That means this is a gradient field. So what's happening in this problem is since P and Q are the same, the starting points and the ending point are the same points, we're just getting getting the difference of the gradient at those 2 points. When I say this is a gradient field, that means that this vector field is the gradient of some potential function. So what we mean when we say it's a gradient field, that means the vector field is the gradient for some potential function f. The integral over a closed curve of any conservative vector field will always be 0. So 2i plus 1j is 2i plus 1j is a gradient field for some potential function. There's some scalar function f of x, y, and this is the gradient of that function. If we want to figure out what that is, we could just kind of brute force it. We're saying that fx of xy is 2. And so that means f by itself must have a 2x in it. So the function by itself has to have a term that looks like 2x. If the j term is 1, that means the partial with respect to y of xy must equal 1. That means f at xy must look like 1y. Now, these two don't match. 2x and 1y are not the same function, but we have to remember that there's a constant of integration. So it's f at xy is equal to 2x plus some constant. This is a partial derivative with respect to x. So this constant might be some constant or some function of only y, because it's partial, it's constant with respect to x. Since it's constant with respect to x, it might be a constant or some function of y. And given the two partial derivatives, that next line saying f of x should look like 1y, we can figure out what that function of y should look like. In the second line, we get f at xy is 1y plus some constant of integration. That constant of integration is constant with respect to y, which means it might be a function of x. So these two things together, it looks like our potential function f should just look like 2x plus 1y plus some other constant. So when we combine these two together, this third c that I've written down, that is just a constant. No function of x, no function of y, just constant. Because the derivative of that c needs to be 0 with respect to x and with respect to y. What this is sitting as an example of is what we have. We have a theorem that concerns this. If we have a line integral of a gradient field, if we calculate a line integral of a gradient field where c is any path from point P to point Q, if the curve over which we integrate a vector field is any path from point P to point Q, then the line integral of a gradient field will just be the difference in the potential function evaluated at those 2 points. Where we ended up on the potential function minus where we started on the potential function. This is the fundamental theorem of calculus for line integrals, sometimes known as the gradient theorem. So if we apply this to a simple closed curve where P and Q are the same point, I'll have f of Q minus another f of, I shouldn't use that one. F of P minus f of P will get 0. This is the fundamental theorem of calculus for line integrals. It is pretty much the same as our normal fundamental theorem of calculus, but instead of gradients of f, we have f prime. Since we can take any path from P to Q, a conservative vector field or a gradient field is called path independent. Gradient fields and conservative vector fields are path independent. Conservative vector fields are path independent. We can take any path from P to Q, and the line integral would just be the difference in the potential function at the endpoints of the path. Path independent or conservative. If a vector field is conservative, then it is a gradient field. That would require proof. I'm going to use proof by authority. It's true. If you don't believe me, I'll switch to proof by threat. You better believe it's true, or I'll flunk you all, the only power that I have. Just believe me. Just trust me. Trust me, it's true. I try not to say that because anybody that's like, oh, trust me, you shouldn't trust, right? Trust me, bro. Trust me, bro. Conservative vector fields are gradient fields. Bro, listen. Bro. Any questions? Correct. 2i plus xj is not a conservative vector field. We would say that is a path-dependent field. It depends on how we take, which path we take through this vector field. It is not the gradient of some potential function. Incidentally, the potential function that we're referring to here, or the conservative that we're referring to here, this is conservation of mass, conservation of energy. It's that conservative. Don't take it as like politically conservative just because I happen to write it in red. I just noticed that.
That's the color that's been used.
Wow. I heard for a while that some schools stopped teachers from marking papers in red because red was such a threatening color. So use something softer like green or something like that. But I think that just changed green to be the bad color in people's minds. Students are like, oh, no, I don't like green. Why not? When we get things wrong, the teacher marks it in green. So if the 2i plus xj, if we tried to find a potential function there, we would not find one. So 2i plus xj is path dependent. I think I called it G yesterday. So 2i plus xj is path dependent. It is not a gradient field. If we tried to find some potential function, then gx of xy would have to look like 2, which means g of x, or xy, would have to look like 2x plus some constant with respect to y. Now that constant could just be a regular old constant or some function of just y, that the partial derivative with respect to x thinks is constant. Gy of xy is x, and that means g of xy would have to look like xy plus some constant with respect to y. Now, it could be that I use C2 for C2, I just use the 2x that we got from the first one, but I don't have an xy in that. If I coming from the gx, I don't have an xy term. I can't have an xy term. I can't use xy as my constant C1. So C2 is equal to 2x, that's fine, but C1 as xy, I can't do that. That's not acceptable. So g of xy is path dependent. We also knew that this was going to be the case because yesterday we calculated the line integral around a closed loop and came up with something that wasn't zero. Any questions? How's everybody okay? Everybody looks super stoked. Y'all look like this. This is the fundamental theorem of calculus. Here we are back in the fundamental theorem of calculus. The structure is the same if we think of the gradient of f as like the derivative of f, but when we're all going at weirdo. Makes sense. One of the first things that we did when we had vectors and partial derivatives, we combined them to make the gradient. So that was like our first derivative. And we notice that the structure is the same as our traditional fundamental theorem of calculus. We just trade the boring old interval from A to B as some path from P to Q, or any path from P to Q. And we trade our f prime of x dx with the gradient of f dot dr. And it's just evaluating the function at the endpoints. Questions? Comment?
Yes.
Remark?
It all come back to the fundamental. That's why it's called that.
That is why it is called the fundamental theorem. The structure of the fundamental theorem of calculus is that we integrate some sets. We integrate some derivative over some set by evaluating the function at the endpoints. So we're integrating the derivative over some set. And what we end up doing is evaluating the function at the endpoints. In our starter set fundamental theorem of calculus, the set over which we integrate is the interval from A to B. Instead of endpoints, I want to say boundary. So we integrate the derivative over some set by evaluating the function at the boundary of the set. We don't phrase it like this back in Calc 1 because the set over which we integrate is an interval and the boundary is just the endpoints. We don't phrase it so much like in the fundamental theorem of calculus for line integrals or the gradient theorem because the set over which we are integrating is just some curve and the boundary is just the endpoints of that curve. But there are going to be more fundamental theorems of calculus when instead of just integrating over a curve, we integrate over a surface or integrate over a solid. So there are two more fundamental theorems of calculus. Any questions? How's everybody okay? So in this structure, we're looking at the in a line integral. The set that over which we integrate is just some curve, any curve from point P to point Q. The derivative can be thought of as the gradient. So in a line integral, C is the set over which we integrate. The gradient of some function is like the derivative. The dx is some small piece of this set, just like dr is some small piece of our curve. And we're just looking at the function at the boundary. Questions? Here's what we noticed about these calculations. The tricky part of this calculation is how messy the integration can get. That's number one as far as the calculation goes. The second part of the trickiness of the calculation I hid from you this week. I hid that all week because we just kept integrating with just different parts of the same curve. The other part is knowing how to parameterize the curve. In this case, we just picked a circle and we just kept integrating over that because we were working mechanics. So the next part, the other tricky part is being able to parameterize the curve. How are we going to describe the set over which we're integrating so that the integral will understand what we're trying to do? That's the other tricky part. The part that we haven't touched on almost at all is what does the line integral represent? That's a difficult question because there are a lot of things that we could use with the dot product. What can we calculate with the dot product? And in that calculation, how does one of those factors show up as continuously variable? So those are the things that we need to think about. But from just the math standpoint, integration is multiplication, but one of the factors is continuously variable. In a line integral, we're integrating a vector field over a one-dimensional curve. The multiplication is a dot product. Our canonical example is work is equal to force dot distance. Work is equal to force dot distance. The work is equal to force times distance that we had from Calc 2. That made sure that the force and the distance were all lined up. Force is gravity, and we're pulling against the gravity. We're just pulling against the gravity. Even if we were pulling something along a surface, we only cared about what was going on with the gravity. So that's why all of your force is equal to work times distance example problems in Calc 2 were lifting things up. Because then there's like the force is pushing down, right? The force is in the same direction and that will pull it. We like that one because we take our force times distance where everything's all in the same direction, and we have force dot distance. Now our force can be applied in any direction. Dot product is multiplication at an angle. So when you're asking about applications of integration, think what are the applications of multiplication? When you ask for applications of line integrals, what are the applications of dot products? All right, that's going to do it for today. These are the things that we want to think about. Different kinds of vector fields, path dependent, path independent. Path independent vector field is called conservative, and it is a gradient field. That's it for today. I will see you all on tomorrow. Everybody have a good day, and thanks for playing.
I,